Hey everyone, my name is BrianSingh, and this is my final presentation for Data605. Sorry, I couldn't attend classes this semester between getting home at 7 p.m. from work in the city every day and taking care of a now 14-month-old. But yeah, anyway, I'll quickly walk through what I did based on the asks. So I know for problem one, it wants us to first generate a random variable capital X that has 10,000 continuous random uniform values between 5 and 15. Yeah, I just do that running the runif function, simple. Then wants us to generate a random population of 10,000 values with a mean of 10 and a standard deviation of 2.89 using R norm. Can do that so right here for capital Y. Then it wants to get into probabilities using lowercase x and y as the medians of the randomly generated values up here, capital X and Y, and investigate whether the probability of value in the population is greater than the median. Just running through that quickly, simply asking, for instance, this first one, the proportion of the x values that are greater than the median of the x, capital X and Y, to the proportion of the x values, capital X values that are greater than a median of y. So, just based on the asks, just performing all of that. And after running the three probabilities that are asked of us, just check whether the joint and marginal probabilities are the same by building a table and evaluating. In doing so, we can see the actual joint and marginal probabilities are more or less the same, with 25% probabilities of each of the true positives and true negatives within A through C. And then, yeah, just running the product of those, you can see again, you get exactly almost the same values. So, it then asks, to see if independence holds using the Fisher's exact and the chi-square test. The difference between the two and which is most appropriate. So both are, essentially just a goodness of fit test. The chi-square is usually used for larger samples, and the Fisher's is, better for smaller samples, though they work in a similar fashion. They compare, the observed values and expected values if the variables are independent. And the bigger the difference, the more likely what we observed is not due to chance. You know, they looking at the results, they both give a p-value of 0.7949. Therefore, we can't reject the null hypothesis that there's a statistical significance in the population. Essentially it's just randomly generated values dispersed amongst a finite range with equal and joint and marginal probabilities. Therefore, not too surprising. So that was problem one. Quickly, problem two wants us to get the data set from Kaggle for the crab age data sets. Again, I just downloaded it and stored it to my GitHub. I'm sure there's a way to pull it right from Kaggle, but this was a little more familiar to me. Yeah, so then just looking at some summary statistics, we can see, sex, length, age, diameter, height, weight, struct weight, visceral weight, and then, age is in the training set, of course, but not within the test. It's the value we want to predict on. So, just going through some plots, looking at some box plots, we can see the distribution is centered around 10 for age, with some outliers to the right here. And again, height is definitely way more, a large outlier here. Again, ID should have been probably excluded, so I should have done that actually, but yeah, more or less ignore that. So we can see get a sense of the distributions and outliers based on the data here. Again, just running some histograms, you can see again just ignore ID, but yeah, there's some normality within the data. Height is left skewed, pretty large, length, to the right, diameter to the right slightly, weight to the left. All of these weights, I guess they're all correlated, but they're all skewed to the left. So yeah, that was pretty much the plots. And here's a scatter plot just to show each of them, comparing them to age on the y-axis here, showing how they behave as x increases, in this case diameter, height. You can see some kind of correlations here. The weights are not distributed based on this pretty not normally, so it's all over the place. The problem then wants us to just do some correlation matrices and hypothesis testing. So I run the correlations between diameter, height, and age, setting the 80% confidence interval as asked. And I can see essentially we have some strong correlations between height and diameter. Where is it? Yeah, here. So height and diameter correlation of 0.92, of course, matches the correlation matrix up here. These between diameter and age and height and age, not too strong, but still above 50%. Yeah, so essentially that's the 80% confidence interval is the upper and lower bounds that it gives us. Sorry, I should have touched on that before. It just states that we're 80% confident that the correlations between the variables fall within this range, which we can see it does. So that's that. The next, then I believe there was another question about family wiser, and yeah, I know I had to Google that a little bit. And it states that the probability of a false positive when running multiple hypothesis tests at the same time, there's a larger risk. And we did perform multiple tests at the same time, therefore I assume it'd be a concern. And again, I'm not too familiar, therefore I don't want to speak too much into it. I did see there are ways to adjust the tests using different methods. Again, not too familiar to delve too deep into that. Yeah, so the next part of the problem 2, it wants us to invert the correlation matrix above, which essentially creates a precision matrix. Then multiply the correlation times precision and precision times correlation, and perform factorization using the lower upward decomposition. Now when we run that, we can see the ones across the diagonal, which is what should be done, and the factorization of the lower triangle and the upper triangle here. The next part of the problem wants us to select a variable that's right skewed, and if you look at the histograms above, you can see that length is and then it wants us to axis to shift if necessary. I don't think it's necessary in this case. All the values are above 0. And then it wants us to fit an exponential probability density function using the fit distribution method. And yeah, it just has a Google on how to do that quickly, not hard. So I chose, again, length, and I passed the skewed variable, which is, I wanted to assign it, to its own variable, and passed it through the functions. And then, after doing that, I'm able to extract the lambda, the optimal rate, based on the exponential distribution. And yeah, as the problem mentions, randomly generate a sample to take 1,000 samples from the distribution, and then compare the histograms so we can see the probabilities of the exponential. We tend to see more smaller values than large, and in comparison, the exponential distribution is showing a pretty rapid decrease as length increases, whereas the original data, you see more of a normal kind of distribution, and it increases towards 1.5 and decreases again at 2, nothing past 2 or a little past 2, and whereas the exponential, you have some outliers here behaving a little randomly. So again, the problem wants us to use the exponential distribution, so to calculate the CDF, the percentiles for the CDF, which is cumulative density function. Again, just using the rate from the exponential distribution, and calculating the 5% and 95th percentiles. So what this is telling us is that in essentially this case, 5% of the lengths in the population, are greater than, or I should not greater than, less than or equal to 0.067, and 95% lie below 3.9. And again, this is based on the exponential, using exponential distribution. So then it wants us to calculate just the confidence interval based on that, and the 95% confidence interval is just telling us that we're 95% confident that the mean of length in the population is between these two values, 0.75 and 1.88 or 1.9. Then using the original data, which is empirical. Yeah, I had to just make sure that was right. Using that to calculate the 5th and 95th percentiles, we can see it's much different than the exponential distribution, with 5% below 0.74 and 95% of the values below 1.68. The exponential distribution may not be accounting for the variability in the data, is my interpretation from that. Then the last part just wants us to build a model and submit to the competition board on Kaggle. And I was trying to just hand select some variables to predict age before. So I know that was one way to do it. I didn't really get too much of a different result, but I thought there was some stepwise methods. So essentially, just using all of the variables, it'll essentially iterate through and determine the best selection for your model, the best fit, I should say. So just taking a look at that, we can see that the model summary down here has a p-value well below the 0.05 significance, and the multiple R squared is okay. It's doing an okay job explaining variations in the estimators. And plot the residuals here. Based on that, you can see some kind of normal distribution. I should have added the line, but essentially above and below the line, most of it is favoring the residuals above the line, so it could be fitted a little better. You can see that here as well. The QQ plot, not a perfectly diagonal line, but some outliers, affecting the performance of the model. So just doing that, the residual mean squared error is pretty low, which is a good thing. So just wanted to take a look at that value. Then I ran the predictions, and just submitted to Kaggle based on what it wanted. I know it wanted ID and age as the two columns, the data frame, probably how they interpret it when they run it through. And this is just a screenshot of submission and my score, username BrianSingh 7, and a score of 1.48. And that's pretty much it. And hope everyone has a great holiday. Any feedback is definitely welcome. This is new to me, not new, but I'm definitely learning, and it is challenging. So I'll definitely welcome all feedback on what I just went through. All right. Thank you.